Welcome back to the Deep Dive. Today we're taking on one of those topics that seems simple on the surface but gets incredibly complex when you aim for professional-grade execution.
That's right. We're talking about building a secure network in Google Cloud. And, the sources you've sent over are fantastic. They're not just a how-to, they're really the architect's playbook.
Exactly. And that's our mission today. We're going to distill the core choices that separate, a quick and dirty network from a truly enterprise-grade, secure, and resilient virtual private cloud, a VPC.
It's all about getting that granular control and shrinking the attack surface down to the absolute minimum. We're digging into the why behind the configs.
So if you're with us on this deep dive, by the end, you could have a really clear mental model for building a network the right way.
Fundamentally, it comes down to control and identity.
All right.
If you can't control your boundaries and you're not using identity as your main security tool, you're already behind.
Okay, let's get into it. So let's start at the absolute top of the pyramid. Resource management in GCP. The source material really hammers this home. Everything, and I mean every single thing, lives inside a GCP project.
And that's a concept that a lot of people new to the platform kind of gloss over. They think of it as just a folder, a way to organize things.
But it's so much more than that, isn't it?
Yeah.
Architecturally, what's its real job?
It's the fundamental unit of isolation. That's the key. It creates a hard, non-negotiable boundary for two things every enterprise cares about: billing and permissions.
Right, so you can see exactly what the dev team is spending.
And you can make sure the dev team can't possibly touch production resources. That project boundary is your first and, honestly, one of your strongest lines of defense.
But the sources also point out pretty quickly that in the real world, projects don't just float around in space. There's a structure above them.
Oh, absolutely. In any company of any real size, you're going to have a strict resource hierarchy. You have to think of it like an org chart for your cloud.
Okay, so walk me through that.
At the very top, you have the organization node. That's the whole company. Underneath that, you have folders, which might represent departments like finance or engineering, or environments like production and development.
And then the projects live inside those folders.
Exactly. And the reason this matters so much to a network architect is one critical concept:
Inheritance.
policy inheritance. This is where things get really powerful.
It's arguably the most powerful security lever you have. Policies, especially organization policies, they don't just stay where you set them. They trickle down.
Trickle down. So if I set a policy at a folder level,
It applies automatically to every single project inside that folder.
Right.
Let's say you create a policy on your production folder that says no VMs can have public IP addresses, period.
okay.
Now, a developer working in a project inside that folder can try all day to launch a VM with a public IP. It will fail every time. The folder's policy overrides their local permissions. That's a huge deal. But it also sounds like it could be a real headache to debug if you're not aware of it. You could spend hours checking IAM roles in your project.
When the real block is 3 levels up in the hierarchy. Exactly. That's the architect's mindset. When you hit a constraint, you don't look down, you look up. What policy did my parent folder hand down to me?
It's about understanding the guardrails that were built before you even started laying down your network.
You got it.
Okay, so now we're inside our project. We understand the policies from above, and it's time to build the actual VPC. The sources are, well, they're not subtle about this. They say you must use custom mode.
Non-negotiable. This is the first real decision you make, and there's only one right answer for any serious workload. You use custom mode.
Why is the default, or what's called auto mode, so bad? It sounds convenient, right? It makes subnets for you.
It is the definition of convenience at the cost of security. It's an anti-pattern, a huge one.
Okay, break that down for me. What does it actually do that's so dangerous?
When you click auto mode, GCP helpfully creates a subnet for you in every single region it has.
Wait, every region? Globally?
Every single one. And worse, any new region that GCP launches in the future, boom, you get a new subnet there too, automatically.
So let me get this straight. I'm building an app that's only ever going to run in, say, US East 1, and with one click, I've just created network infrastructure in Asia, Europe, Australia.
All over the world. Idle, unmanaged, unmonitored network exposure. You have just completely violated the principle of least privilege.
Because I've provisioned dozens of things I have absolutely no need for.
And each one is a potential attack surface. It's something else you have to audit, manage, and worry about. Custom mode is the only professional choice because you start with nothing, a blank canvas, and you, the architect, explicitly define only the regions and IP ranges you need.
Nothing more.
Nothing more. You build the smallest, tightest perimeter possible from day one. That's what control looks like.
Okay, so we've chosen custom mode. We have our blank canvas. Now we get to the actual art of segmentation. This is where we start carving up the VPC into logical, isolated chunks.
Right, and this is about creating layers of security. We don't want a flat network where everything can talk to everything else. The sources use the classic three-tier app model, which is a great starting point.
So we're talking about a web subnet, an app subnet, and a DB subnet.
Exactly, all within a single region, say US East 1. You're logically separating your front-end servers from your business logic and your business logic from your sensitive data.
And the I key addressing here is key. The guide uses ranges like 10.1, 0.1, 0.2, 0.024, and so on. These are all from the RFC 1918 private space.
And that's a deliberate foundational security choice. By using these private, non-routable IP addresses, you're ensuring that these instances are, by default, completely shielded from the public internet.
To get to them, you'd have to do something very explicit, like assign a public IP or set up a load balancer.
Precisely. You are in complete control of what is and is not exposed. Nothing gets out and nothing gets in unless you specifically design a path for it. Hashtag tag 2.1 logical tiers and subnet segmentation.
Okay, but this is where a lot of initial designs fall apart, right?
Mm-hmm.
Planning for growth. The sources bring up something called secondary IP ranges. What problem are they solving?
This is where the architect really has to think ahead. Secondary ranges are all about planning for modern containerized workloads, specifically for Google Kubernetes Engine, GKE.
What's so special about GKE that it needs its own IP ranges?
Well, think about what a GKE cluster is. You have your worker nodes, the VMs, right? They take up IP addresses from the subnet's main or primary IP range.
Okay, that makes sense.
But then running on those nodes, you have potentially hundreds of pods, which are your actual application containers. And you have Kubernetes services, which are like internal load balancers for those pods.
And they all need their own IPs, too.
They all need their own IPs, and they can't share the same pool as the nodes. GKE needs dedicated IP ranges for the pods and for the services.
So if I just create a subnet with a single 24 range for my app tier, and then try to deploy a big GKE cluster into it,
You're going to have a very bad day. You'll run out of IP addresses for your pods almost immediately. Your cluster will stop scaling, and you won't be able to deploy new applications.
And what's the fix? Is it easy to add a secondary range later?
It is painful. Very painful. In some cases, you basically have to tear down the entire subnet and everything in it and start over just to add the required IP space. It's a rookie mistake with massive consequences.
So the architect's job is to calculate that capacity from day one.
Yeah.
You need space for your VMs and for all the container components that'll run on top of them.
That's thinking like an architect. You plan for the future state, not just the present one. Hashtag tag 2.2, unpacking private Google access, PGA.
Okay, this next point in the material is fascinating because it seems like a direct contradiction. It's about a feature called Private Google Access, or PGA.
Yeah.
The beginner's guide might say, just leave it off. But the architect's notes say, you should almost always enable this for production. Why the huge difference in opinion?
This is the difference between thinking about pure network isolation versus secure operational design. The beginner thinks, my database is private, it shouldn't talk to anything.
But the architect knows that even the most secure database needs to do things.
Exactly. It needs to send its audit logs to cloud logging. It needs to write its encrypted backups to cloud storage. Those are essential operational tasks.
And cloud storage and cloud logging are Google services with public API endpoints.
Right. So now you have a paradox. Your database only has a private IP, 10.nano.3.5. How does it securely reach the public endpoint for cloud storage without you punching a giant hole in your security by giving it a public IP?
That's the question. How do you do it?
That is exactly what Private Google Access solves. When you enable PGA on a subnet, you're telling GCP for any VM in here that only has a private IP if it tries to talk to a Google API.
Like cloud storage.
Don't send that traffic out to the public internet. Instead, route it internally across Google's own private backbone network directly to the service.
So the traffic never even touches the public internet.
Never. It's a secure private path from your private VM to a Google managed service. It's a massive security win, especially for compliance. You get the functionality you need without compromising your no external IP security posture.
That makes so much sense. So for any real-world workload, you're going to need PGA.
Almost certainly. And this sets up the next big question, which is, what if that private VM needs to talk to something that isn't a Google API, like a third-party software repository?
Right. PGA can't help with that.
No. And for that, we need a totally different tool.
Okay, so our network is designed, it's segmented, and we've enabled secure access to internal Google services with PGA. Now it's time to build the gates themselves, the VPC firewall rules.
This is where we get explicit about what traffic is allowed to move where. And before you write a single rule, you have to burn the default behavior into your brain.
Yes, this is a classic exam question, right? The
Yeah.
two implicit rules. Let's start with ingress traffic coming in.
Ingress traffic is, by default, implicitly denied. This is a good thing. It's a secure by default posture. If you do nothing, nothing can get into your VPC.
Okay, safe so far. But what about egress traffic going out?
And that's the dangerous one. Egress is implicitly allowed.
So any VM I launch, out of the box, can phone home to anywhere on the entire internet.
Anywhere. 0.0.000. It can initiate connections to anywhere it wants. For any kind of high security or compliance environment, that is a 5-alarm fire. It's the first thing you have to fix. Hashtag 3.2 key ingress rules for access and application flow.
That's a great setup for why we need to be so deliberate with our rules.
All right.
Let's look at the first one from the guide, securing administrative access with allow shimmer from IAM.
Right. And this rule immediately shows an architect-level choice. We're moving away from the old, clunky bastion host model.
The bastion host being that one sacrificial VM with a public IP that you have to jump through to get into your private network.
Mm-hmm. And you have to patch it and monitor it and manage its keys, and it's a pain. The modern, secure way is using the Identity-Aware Proxy, or IAP.
And the clue that we're using IAP is right there in the firewall rule itself, isn't it?
It is. It's the source IP range, 35.235.240.020. That's not a random range. That is the specific published IP block that Google's IAP service uses.
So this rule says only allow SSH traffic if it originates from Google's own managed IAP service.
Exactly. You're no longer relying on a network location for security. You're relying on Google to authenticate the user's identity through IAM before it even lets the traffic into the tunnel. The security perimeter has shifted from the network port to the user's actual identity.
Much, much stronger. Okay, rule number 2. Allow HTTP-HTTPS-web. This one targets web servers and allows traffic from 0.0.00, the whole internet. Now I have to call this out. For a secure guide, that feels wrong.
It is wrong. And you're right to question it. The guide puts it in there as a basic example, but immediately follows up with a security critique. In a real production setup, you would never, ever use 0.0.0000 as the source for your web tier.
Why not?
Because your web tier shouldn't be directly exposed to the internet. It should be sitting behind a managed global external load balancer.
Okay. So the traffic hits the load balancer first.
Right. And the load balancer then forwards the traffic to your backend VMs. So from your VM's perspective, where does the traffic actually come from?
It comes from the load balancer.
It comes from the Google front end, the GFE, which has its own specific IP ranges. A proper architect's rule would replace 0.0.0.00 with that much smaller specific GFE range.
And why is that distinction so critical?
Because you need to force all traffic to go through your load balancer. That's where your other security tools, like your web application firewall, Cloud Armor, live.
Yeah.
If you leave the firewall open to the whole internet, a clever attacker could try to find your VM's IP address and bypass your load balancer and all of its security protections entirely.
So the firewall rule enforces the architectural flow. Brilliant. Okay, that brings us to the internal rule, allow app to DB, which leads to the huge debate, tags versus service accounts.
This is maybe the most important concept in the whole deep dive. If you want to pass a professional exam or build a truly secure network, you have to nail this down.
So let's start with tags. They seem easy. You just put a label like app server on a VM. What's the problem?
The problem is that a tag is just metadata. It's a post-it note. It's not a secure identity. Anyone with a fairly common permission, instance admin, can change the tags on a VM.
So an attacker, or even just a careless admin, could take a random VM, slap the app server tag on it.
And instantly, your firewall rule lets it connect to your production database. The tag has no real tie to the machine's actual identity or purpose. It's too mutable, too easy to misuse.
Okay, so that brings us to the gold standard. Service accounts. How are they different?
A service account is a true identity managed by IAM, the core security and identity service for all of Google Cloud. It's like a passport for the VM.
And it's much harder to change.
It's strictly controlled by IAM policies. So when you rate your firewall rule, instead of saying allow traffic from any VM with this tag, you say allow traffic only from a VM presenting this specific service account identity.
You're tying the network access rule directly to the core identity platform.
That's it. That is the definition of identity-based segmentation. You stop trusting flimsy network labels and start trusting verifiable, cryptographically signed identities. If a VM service account changes, its network access changes instantly, automatically. It's a fundamentally more secure model. Hashtag 3.4, implementing strict egress control.
Let's circle back to that terrifying default egress rule, the one that lets every VM talk to the whole internet. How do we, as architects, slam that door shut?
We have to play a game with priority numbers. Firewall rules are evaluated in order from the lowest number, which is the highest priority, to the highest number.
The implicit allow all rule sits at the very bottom, at priority 65535.
Exactly. So to override it, we need to create an explicit deny rule with a higher priority, meaning a lower number.
So we start by blocking everything.
Yes. You create a rule called something like deny all egress. You give it a high priority, like 65534. You set the destination to 0.0.0.00 for all protocols, and you set the action to DENY.
And because that rule has a higher priority than the implicit allow, it wins. Now everything is locked down.
Complete lockdown. No VM can talk to the outside world by default.
And now we can be extremely precise about the exceptions. If my web servers need to get security patches from the internet.
Now you create another rule, an allow rule. You give it a much lower priority number, something like 1,000. You name it allow web egress updates.
And you target it very specifically.
Very specifically. You say this rule applies only to VMs with the web service account, and it only allows outbound traffic on TCP port 443. Anything that doesn't match that very specific rule falls through, hits your deny rule at 65534, and is blocked.
And just like that, you've met a core PCI DSS requirement. Controlled, audited, and explicit outbound access only.
That's architect-grade egress control. For the highest level of security, the sources note you'd even block that and force all access through something called VPC service controls. But for most use cases, this deny-first strategy is the foundation.
All right, this is the fun part. We've got all the pieces. Let's put them together and walk through that secure e-commerce blueprint from the sources. This is where theory becomes practice.
This is where it all clicks. You see how these individual decisions create a layered defense. Hashtag 4.1 application flow breakdown.
Okay, let's follow a user's request. It comes in from the internet, and the first thing it hits is our web tier. What's happening here?
So the web tier is in its own web subnet. Its only job is to handle those incoming HTTP and HTTPS requests. But as we established, it's not just sitting there with a public IP, it's behind a global external load balancer.
Which means our firewall rule for this tier is locked down to only accept traffic from the Google front-end's IP range.
Correct. We're forcing every packet through our security checkpoint, the load balancer, with cloud armor. The web VMs themselves are effectively hidden with no direct path from the internet.
So that's layer one. If that web server gets compromised, what's the next hurdle for an attacker?
The next hurdle is the application tier, sitting in its app subnet. This is where the real business logic lives. The payment processing, the user session management. It is completely, totally inaccessible from the public internet.
Its only way in is from the web tier.
The only ingress it allows is from VMs with the web server identity, and its only allowed egress is to one place. The database tier on a specific port, like 3306 for MySQL.
So the attacker on the web server can't just scan the network or connect to the database. They're trapped in that middle segment.
Right. They'd have to find a second vulnerability in the application itself to pivot further. And all the while, the crown jewels, the data, are sitting in the final layer, the database tier.
In the DB subnet.
The most protected part of the network. It only accepts connections from the app server identity. It has no external IP. And our strict egress firewall rule ensures it can't initiate any outbound connections, except perhaps to cloud logging via private Google access for its audit trails.
It's a fortress. It only talks to one specific thing in one specific way.
That's defense in depth. Hashtag 4.2 microservices and identity-based segmentation.
This three-tier model is a great classic, but what about the modern world? The sources bring up a financial institution with hundreds of microservices. How does this model scale?
It doesn't, not if you're thinking about IP ranges. You can't manage firewall rules for hundreds of constantly changing IP addresses as services auto-scale up and down. It's impossible.
This is where the shift to identity becomes the only viable path.
It's the only way. You stop caring about the IP address. It's ephemeral. It doesn't matter. What matters is the service's identity. So you have a payment service and a user profile service.
And each one gets its own service account, payment say, and user profile SAM.
Precisely. And you isolate them logically, maybe in different GKE namespaces. Now, let's say the user profile service needs to call the payment service to get a transaction history.
How do you write that firewall rule?
You write an identity-based rule. The rule says, allow traffic on port 8080. The target of this rule is any VM running with the payment say service account, and the source is only VMs running with the user profile say service account.
That is so powerful. So if some other service, say the inventory service, gets compromised, it doesn't matter that it's on the same network.
It can scream at the payment service all day long. The firewall will drop every single packet because it doesn't have the right passport, the user profile say identity.
This is what identity-based segmentation really means in practice.
Yes, and then you only expose a tiny fraction of these services, maybe a single API gateway service, to the outside world through a load balancer. Everything else is internal only, protected by these strict identity-based rules. Your attack surface just shrank by 99%.
Okay, let's shift up a level. We're now moving into the patterns that solve big organizational scale problems, the stuff you only run into when you're dealing with dozens of teams and hybrid cloud setups.
First up is shared VPC. This is the go-to pattern when you have this classic organizational tension. You want centralized control over the network, but you want developers to be able to move fast.
So separation of duties.
Exactly. Imagine you have a central network security team and 20 different application teams. You can't have 20 different teams making up their own firewall rules and IP schemes. It would be chaos.
You need a single, consistent standard.
So you implement shared VPC. You have one special project called the host project. This is owned by the central network team. It contains the VPC, the subnets, the firewalls, all the core infrastructure.
Okay, so that's the centralization part. Where does the delegation come in?
The application teams get their own projects called service projects. These projects are then attached to the host project.
What can the developers in those service projects do?
They get a special IAM role that lets them use the subnets from the host project. They can launch their VMs, their GKE clusters, their databases into the centrally managed network. But critically, they cannot change the network.
They can't delete a subnet or modify a firewall rule?
Nope. They are consumers of the network, not managers of it. The central team sets the secure guardrails, and the dev teams get the agility of self-service resource deployment within those safe boundaries. It's the best of both worlds. #tag 5.2 VPC peering and the golden rule of non-transitivity.
Okay, next pattern. Connecting our network to someone else's, like a SaaS provider who is also on GCP. We use VPC peering. But the sources have a huge warning label on this one.
The golden rule. Peering is not transitive. If you remember nothing else, remember that.
Explain what that means. A peers with B, and B peers with C. In the normal world, A should be able to get to C through B.
It feels like it should work that way, but it absolutely does not. In GCP, a peering connection is a strict one-to-one relationship. VPC-A learns the routes for VPC-B's subnets, and that's it. VPC-B will not then re-advertise A's routes to its other peer, VPC-C.
So B acts like a dead end, not a router.
A perfect way to put it, it's an endpoint, not a transit hub. And this causes all sorts of confusion, especially in hybrid scenarios.
Which is challenge 3 in the guide. We have our VPC-A, which is connected to our on-prem office with a VPN. We then peer VPC-A with VPC-B. The team using VPC-B wants to hit a server in the office.
And they can't. The connection just fails. From VPC-B's perspective, it knows about A's cloud subnets, but it has zero knowledge of that VPN route to the on-prem network. VPC-A will not forward traffic from B into its VPN tunnel.
It's blocked. So what's the architectural fix for that?
You have a few options. The simple but clunky one is that VPC-B has to have its own separate VPN connection to the on-prem network.
Which means more cost and complexity.
Right. The more elegant modern solution is to move to a proper hub-and-spoke architecture using something like Google's Network Connectivity Center, or to redesign using shared VPC, where that central VPN connection in the host project is automatically available to all the service projects. #tag 5.3 hierarchical firewall policies, HFP.
All right, let's talk about enforcement at a massive scale. I'm the CISO. I have 1,000 projects. I need to make sure that nobody ever opens RDP, port 3389, to the entire internet. How do I enforce that everywhere? Guaranteed.
This is the job for hierarchical firewall policies, or HFPs. They are the ultimate top-down security control.
How are they different from the regular VPC firewalls we talked about?
Regular firewalls live inside a project. HFPs live above the projects at the organization or folder level.
So they get inherited, just like the organization policies we discussed at the start.
Exactly. And crucially, they override local VPC rules. If you set an HFP at the organization level that denies port 3389 from 0.0.000,
A local admin in a project can try to create a rule to allow it, and it won't matter.
the HFP wins. The traffic will be blocked. It provides that absolute non-bypassable security baseline for the entire company.
But this leads to the classic security versus agility problem. Challenge 1 in the material. My company bans FTP, port 21, globally. But a small team in the legacy dev folder needs to allow it for a very specific, temporary test.
Right. You can't just turn off the global ban, but you need a surgical exception. This is where the true power and complexity of HFPs comes in with a command called go to next.
Go to next. What does that do?
It allows you to delegate the decision. You set up your rules in layers. At the very top, the organization level, you might have a rule at priority 10 that says DNY port 21.
Okay, that's the global ban.
But you create another rule with a higher priority, say priority 5, that says if the traffic is destined for a project inside the legacy dev folder, then action is go to next.
So the packet comes in, the firewall checks the rules, sees it's heading to that special folder, and instead of hitting the DNY rule at priority 10, it hits the go to next rule at priority 5 and is told, what?
It's told to basically ignore the rest of the rules at this level and continue the evaluation down at the next level on the hierarchy, which is the folder.
Ah, so you've passed the baton down to the folder.
Exactly. And then at the legacy dev folder level, you can create a local HFP rule that explicitly allows port 21 from your specific testing IP. All other traffic to all other folders still gets blocked by the global deny rule. It's complex, but it's how you manage enterprise-wide policy with real-world exceptions.
For our last pattern, we need to really nail the difference between two services that sound similar but do very different things. CloudNet versus private Google Access.
This is a critical distinction. They both provide outbound connectivity for private instances, but the destination is completely different.
Okay, let's go back to our private GKE nodes. They have no public IPs. They need to download a critical security patch from, say, the official Ubuntu package repository, which is just out there on the public internet.
Right, so we've already established what PGA does. If we enable PGA on that subnet, can those nodes get the patch?
No, because PGA is only for connecting to Google APIs like Cloud Storage or BigQuery. It can't reach a third-party server on the general internet.
Correct. PGA fails to solve this problem, so we need a service that can take traffic from a private IP, send it out to the public internet, and get the response back, but, and this is the key, do it without ever exposing the private instance to inbound connections from the internet.
And that is the exact job description for CloudNet.
That's it. CloudNet is a managed network address translation service. You enable it on your VPC router. When your private GKE node sends a packet to the Ubuntu repository, CloudNet intercepts it, replaces the private source IP with one of its own public IPs, and sends it on its way.
And the response comes back from the repository.
CloudNet remembers the connection, translates the IP back to the private GKE node's address, and forwards it internally. From the internet's perspective, it never sees your private IP. It only ever talks to the CloudNet gateway.
It's completely one-way, outbound, initiated traffic. No one on the internet can start a new connection into my private node through the NAT.
That's the security model. It lets your private resources get what they need from the outside world without compromising their protected private status.
So the simple rule is PGA for private access to Google, CloudNet for private access to everything else on the internet.
If you get that, you've grasped a core concept of secure cloud networking. #outro.
That was an incredible tour. We really broke down what it means to think like a security architect. We started with the absolute mandate of using a custom mode VPC for control.
And we drove home that auto mode is just an anti-pattern, creating a massive, unnecessary attack surface from the start.
We talked about segmentation, but more importantly, about moving beyond simple network tags to using verifiable identity with service accounts as the basis for all your firewall rules.
That's that shift to identity-based segmentation. It's the future of network security.
And then we hit those big organizational patterns, using shared VPC to centralize control while delegating work, remembering that golden rule that VPC peering is never, ever transitive.
And using hierarchical firewall policies as that top-down enforcement hammer to set security baselines that no one can bypass.
And finally, we really clarified that crucial difference. PGA gets your private instances to Google services, and CloudNet gets them to the rest of the internet securely.
I think the biggest takeaway really is that cloud security is hierarchical. It's not about drawing lines on a network diagram anymore. It's about identity and policy that flows from the top down.
The architect's job is to define the boundaries, and more importantly, to define the identities that are allowed to cross them.
You've got it.
Which brings us to our final thought for you to take away. We saw how hierarchical firewall policies can enforce a strict company-wide security posture, but they also have complex exception mechanisms like GoToNext. So, as you design your own global policies, you have to ask, when does the undeniable security benefit of a company-wide deny-all rule outweigh the operational risk of introducing a complex, multi-layered exception system that has to be configured perfectly to avoid accidentally blocking legitimate work for your development teams?
That's the tightrope walk between security and agility right there. Something to think about.
Thank you for joining us for this deep dive. We'll see you next time.